Okay, so hello everyone. This is going to be, I guess, the part two of kind of this. It should be the last lecture. I think I should be able to squeeze everything in today on kind of spin-adapted electronic structure. This new recipe for spin-adapted electronic structure on quantum computers. We use representation theory, in particular this group product of UD cross SU2. So quantum chemistry, we have spin orbitals. So you have spatial orbitals with two spins. So the D is the number of spatial orbitals, and the SU2 is the spin part. Then this is the work between myself and Jed. Jed's not here because he was awake till 3:30 last night working on the paper, which is yeah. I didn't force him to do that. He just did it out of his own goodwill, I guess. And the paper's hopefully we'll have a draft in the next week or so. So yes. So yeah, and then my contribution, I would say, is more on representation theory, underlying foundations, and Jed did most of the quantum algorithm development and some of the potential, like more quantum information applications that are in the paper. So this, hopefully, with this talk, like I'm going to provide intuition for the paper. The paper is very detailed. We go to a lot of efforts to kind of rigorously prove lots of the identities first solved by Paldus and Shavitt and people like that. So we really take a mathematical physics approach to that, but we're going to state some of the results and some of the rough outlines of the proof. But if you want more details, they'll be in the paper. Okay, so I gave this talk at this Quantum Digital Twins conference on Friday, but I actually thought it was a really nice kind of. It's actually very apt, I think, because actually we have to give this definition of what a quantum digital twin was. And really, I think my opinion, coming from a symmetry background, is quantum algorithm that incorporates at a minimum all the global symmetries. Okay, so I would argue that if we're just working with fermions and spin orbitals, if we're not incorporating the total spin, we're not really physically simulating the whole system. That's quite a few. So we're going to actually do the global symmetry first observed by Stern-Glatt. And it like these spherically symmetric silver 5s valence ions were shot through a magnetic field, and because they knew about orbital angular momentum at this time, but they didn't expect it to be quantized on some other magnetic property, and they had to. The only thing they could label this with was the spin of the electron. So they called this the spin, this concentration here. And then, kind of the Paldus fusion principle. This is something which we use like throughout this work, is that because no two fermions can have the same quantum number, they essentially sit in the same spatial orbital. This is an anatomical picture, I guess, but you have the three different spatial orbital quantum numbers, and then they have a spin quantum number as well. So basically, what it's saying is that every electron has to sit in a spatial orbital, and it can be spin up or spin down. So yeah, at the end of the talk, hopefully it will present a rigorous framework for transforming the half-spin Fermionic problem into a UD cross SUT spin-adapted basis on a quantum computer. So the motivation for this talk really is when we have this thing up here is that it's the molecular electronic quantum chemistry Hamiltonian presented in the spin-free framework. So you basically pair up so I and J KL here are spatial orbitals, and mu is the spin index. You can basically just pair up the fermionic operators, and then you can sum over the spin, and this gives you what's called the spin-free quantum chemistry Hamiltonian. And essentially, when you evolve this Hamiltonian, there's a very special basis which is blocked on the total particle number. So this is 6 spatial orbitals. So it has three spatial orbitals, which has potential total occupancy of 6 particle numbers. It's blocked on the total it's blocked on the particle number, the total spin, the spin projection, and then there's this D is the dimension in this block. So if you look, can't really see because I guess it's quite green. I think that's frustrating. Yeah, this quite slightly pixelated, but this is the N3 block, particle number 3, and this blue one here. This is the spin 1/2. The spin 1/2 has 2 multiplets of 1/2 and minus 1/2, and then it has 8 dimensions. The spatial orbital part is 8-dimensional. So basically what we'll do is we'll explain by the end of the lecture. You should be able to understand why you get the spin blocking. And this is a physically observed thing, right? Because we're observing the spin quantum numbers here. So really, like the point is that we're trying to do quantum algorithms which work within this inherent physical block structure, spin block structure. And then there's also this. One of the benefits of this is a hidden recursive structure, which leads to these Shavitt graphs you might have heard of. And yeah, I would say that the basis, working in this basis, is very tricky and it's not rigorously understood in quantum computing. So that's it. All we're presenting today really is a basis transformation into the spin blocks formalism. And future work will be block encoding and quantum algorithms that obey this strict spin symmetry. Yeah, and I think it's the true symmetry of the main electronic wave function. Yeah, so like it really is, in my opinion, like this the molecular electronic fermion really obeys this symmetry, not just anti-symmetric symmetry. All right, so yeah, we're going to brief recap because I know that we did a bit of last week. We did 3 weeks ago. We did some. We went over the kind of background. There's a lot. It's a very technical mathematical topic, so I think a review of this is probably it's probably helpful. So if we have a group, then we can always map that group onto its action on a vector space V with a set of general linear matrices, and then it obeys this homomorphism property. So the homomorphism, I don't have time to give you an example, unfortunately, but the homomorphism property essentially is when you map your group element G via rho, the group product is obeyed inside and outside of the map, basically. Yes. So this is basically saying that if the action is the same but the words are different, that's kind of what a nice intuitive description of a homomorphism. So the action is the same but the words are different. There we go. That's the right thing. And then once you have these representations, you have these irreducible representations. So irreducible representation of a group is a representation lambda on a vector space V, such there is no proper non-zero subspace G that invariant by the action of lambda of G on an element in V for all V for all G in G. Okay. So what that's saying is basically you might have some matrix which does the group action rho, but within it, and that will act on this, and that will act on W via the general linear matrices. But there might be some smaller subspace within this matrix which does the same group action and transforms the group elements within that subspace. So W is the big vector space here in this matrix, and the VI's are the subspaces within this. Okay, and you can see that because of this property that all the group elements transform within the subspaces, we can rigorously break down the vector space W into a direct sum of VI over I. So this is really the mathematicians might think about representation in a bit of a different way, but as chemists who are really bothered about vector spaces and matrices, I think this is quite an instructive way to think about like representations. Okay, so it's from a matrix point of view, that's really how I think about it. Okay, so what we're going to do today is we're providing a rigorous breakdown of the Fermionic wave functions, these blocks, like we did on the previous slide before. Okay, yeah, and if you're interested in this, the canonical textbook is this Bolton and Harris. That's pretty intense, that book. And then the characters, so the characters really give us a recipe to kind of play with these, to analyze the representations in quite a neat way. So this is the formal definition of a character. So basically, all this is saying is it's saying the character is the trace of the representation matrix we showed in the previous slide, and they have a nice property that they're constant on the conjugacy class. So basically, what this means is lots of group elements within a group might be part of the same part of the same conjugacy class, and they all have the same character. So it means you might remember this in your character tables in quantum chemistry. It's like this allows you to basically treat a lot of the group elements which have the same behavior on the same footing. And the most important thing, this is really important now, which we'll use throughout this lecture, is that it's additive over the direct sum of the matrix representations. So I guess that's quite intuitive when you think about this direct sum. The character of this is just going to be the sum of this plus the sum of this plus the sum of this. So it's just complete additive across here, the trace of this matrix. Okay, and it's multiplicative over the direct product as well. So it's really powerful because it means you can treat these very complicated matrices acting like arbitrary basis states via the character, which is invariant under basis transformation, by just a simple scalar. And this is really what this is what we use the character to do all these vector space decompositions in this work. And just really quick recap as well, so that the standard. So we're going to be bothered about the unitary group. So the unitary group is the unitary group of n is the group of n by n matrices, which are invertible. So they have a determinant of non-zero, and then they are also unitary. So u dagger u equals is the identity. Yeah, so that this guy, yeah, precisely. And the elements are complex. And the because every matrix in this group is conjugate to a diagonal matrix by some basis transformation, we can parameterize the full set of conjugacy classes on this set of diagonal matrices. Okay, and then the trace is just the diagonal of this diagonalized matrix. So these are parameterized on this theta because this is a complex number, but we just represent these as z. So this is quite abstract, but these are because this is the standard irrep, which is the action of u on its natural vector space, the n-dimensional vector space. This basically gives us a set of parameters which we use to build the larger irreps of un. Okay. Yeah, keep this in mind. I think these diagonal elements are really important for this work. And we represent the standard irrep as this one here. So this is the character of un, and this is saying it's constant on the conjugacy class, and it's represented as single partition one. Okay, so things get a little bit more complicated here. It's quite abstract. I spoke about this last time, but essentially the larger irreps of un, when you take tensor products of the standard irrep and then diagonalize under the Cartan subalgebra, which are the diagonal elements of the Lie algebra of un, you end up with these simultaneous eigenvectors because they're diagonal, which each have their own unique eigenvalue, which is lambda I. Okay, so you get a set of basis states when you do that, and essentially they're all the same up to some permutation of these lambdas, and this basically gives you the set. These weight states are really the set of basis states that live within this basis space here. And then you have what's called the highest weight state, which is the state which you can raise the weights. You can raise the weight states within the weight space, so you can move through them with these operators, these Eij raising operators, and you'll eventually get to a highest weight state, and that will annihilate. And the eigenvalues of that state identify the larger irrep of un. So what that means is, basically, if that didn't mean anything to you, when these Eij operators annihilate on this state lambda, the eigenvalues that you get, they form an ordered tuple, which is represented as a partition. So basically, all I'm saying is that the irreps of un are indexed via the partitions, so this is the Young diagram, they call it, which typically comes from the symmetric group, but there's a very interesting interplay between the unitary group and the symmetric group. But the irreps are, and this is an example of it, the irreps of un are indexed via these partitions. So this 321 is how you represent it. So the irreps come from partitions. That's the summary of this slide. And then there's this very scary looking formula which we won't use. But I'm just having it for completion. So one of the big results from Lie group theory is that the characters of these irreps is calculated by the Weyl character formula, which has a very scary and very weirdly indexed powers of these polynomials. And this is a quotient of polynomials, which gives a real polynomial. It's a very old result. It comes from Cauchy in the 1800s, 1700s, very old. And we actually, in the paper, to do all the proofs, yet we annoyingly have to use this form. But it turns out, for our purposes, yeah, and I would say that if you're interested in this, I've spent a long time reading this book, this Symmetric Functions and Whole Polynomials book by MacDonald. That's really the canonical reference for symmetric polynomials. The thing that's really nice is we showed the isomorphism between this form and the previous equation in the paper, but we said before that the irreps of the unit group are characterized by these Young diagrams, these partitions, and the gods of mathematics, I guess, decided that if you were to fill up these Young diagrams by semi-standard Young tableau conditions, which means that as long as you increase weakly across the rows, which means you can repeat across but also go up, and then increase strictly down the rows, down the columns, where you can't repeat the numbers, and they must be strictly increasing. You end up with all the different ways you can fill these Young diagrams, and these turn out to be these are the basis elements of the representation, but also they're the elements of the trace of the irrep of the unit group, which is very. I think this is very. So this is all we need here basically. So this is a very famous symmetric polynomial called the Shor polynomial, and it's invariance of permutation of the variables. Okay. Now we've made the link now that the characters of the unit group can be represented by these special symmetric polynomials, and really that was the key insight that we had to kind of formalize all of this. Is that you had it means that you can basically treat the representations of the unit group with the very famous identities which come from symmetric polynomial theory, which is 200 years of work in that area, which is very cool. Any questions on this so far? This is all recap. Okay. Yeah. Oh yeah, and importantly, yeah, these. Yeah, that's definitely. Can't forget.
There's one question on that. So in the middle, you've got two tableau fillings which end up with the same term in the polynomial.
Yeah, exactly.
So does that mean it's not a one-to-one mapping or something? I mean, yeah.
Well, I guess it'll tell me
that. I think the way to interpret this is that this is more expressive than this.
Okay, right.
That makes sense.
Yeah, that means it is sort of many to one.
Yes, yeah, exactly. Yeah. So it's definitely better to work in this framework. Yeah, and also these variables x1, x2, x1. So this is a three. So in this example, it's the unit group of 3 by 3 because we only have 3 variables, and these x1, 2, 3. These are the. Sorry, getting slowly back. These are the trace elements here. So if this was this would be a 3 by 3 matrix, and with the diagonal elements. Yeah. Okay. So you don't really care that this parameterizes the quantity class. You just take these as the variables for the characters of the Shor polynomials. Okay. Okay, and then this is just the kind of, I guess, well, we use this a lot in the paper, but the proof is done in the paper, but it's basically showing that there's many identities and rules of combining these polynomials. The famous one is this dual Cauchy rule, where this one we use in the paper, which is where it's basically a rule for combining products of Shor polynomials. So S lambda is one of the Shor polynomials for a partition. So in this case here, this is the 2, 1, and then this EK is a special case of that where you just have a vertical one. And basically, you can form these these short, but you basically form the Young diagrams that correspond to the short polynomials. And as long as you don't add two to the same row, then you get this decomposition. So this basically is taking a direct sum of the characters and forming a direct product of the direct product of the characters and forming a direct sum. So these are the characters which correspond to the representation. So basically, it allows you to take direct products of the representations and form direct sums using the language of the symmetric polynomials. Yeah, and interestingly, these work for infinite number of variables because as long as you can fill up the tableau with the number of variables that you choose, it doesn't matter. But you will get different polynomials if you have different numbers of variables. Yeah, this is more on the side. It's just that says that it's basically showing that it opens up the whole toolbox to kind of decompose these vector spaces. The proof of this is in the appendix, which we went to a lot of effort to do all this stuff. Okay, that's enough recap. So basically, the characters can be interpreted by the short polynomials, which allow representations to be decomposed through the theory of symmetric polynomials. And we can now apply this to the full Fermionic Fock space. And then use this U, it should be D here, but U at UD plus SU2. Okay, so I think this is usually kind of the tensor network notation, but it's essentially each one of these. This is tensor network notation for a wave function. Each one of these legs is an n particle Hilbert space, and there's no symmetry here, so this isn't fermionic or anything. This is just a tensor product, which is and each one of these W's can have any value from 1 to n. And this basically allows you to build a basis states like this, and that the coefficient for each one of these basis functions is stored inside this tensor. And we have k of these n particle Hilbert spaces. And we use this, and interestingly, because you can permute these legs in such a way that W then becomes sigma, Wi becomes sigma I through some permutation of the symmetric group. It carries a representation of the symmetric group for k elements. And the irreps of the symmetric group are also indexed by these Young diagrams. I don't have time to explain this, but you can derive these from the Young symmetrizers, which it's a very unintuitive derivation, to be honest, but yeah. So you get these, so for example, you get this is the symmetric representation, this is the anti-symmetric representation. But also because these single particle Hilbert spaces have dimension n, they can be acted on via a group element of the unit group of n by n unit matrices. So you can represent this via like each basis state gets rotated by some arbitrary unit transformation. And it's a very nice way to represent this. And as we said before, the irreps of this G, when you take this tensor product of these and then block diagonalize, these also have the irreps are also represented by these Young diagrams because the characters are symmetric polynomials, these short polynomials, which can be which these correspond to. Now, so these are in this form these have multiplicities. So you might have multiple copies of these irreps in each one of these decompositions. But there's a very famous duality between the symmetric group of k elements and the unit group of n elements. And this is called Shaw-Weil duality. And it's an example of a double commutator algebra. And this tensor network representation allows you to represent this very elegantly, I think. So you have this T operation, which is a permutation followed by combined with a unitary rotation. You can see the action of the unitary group, tensor product of unitary group elements, followed by permutation, is the same as the permutation followed by the action of the unitary group elements here. Okay, and this is a very, very famous duality called Shaw-Weil duality. So you can see that the outcome is the same, and these actions commute. And when you do this, the irreps get paired up, and the multiplicity spaces get acted on by each group. So yeah, so you basically get this this multiplicity-free decomposition, where the multiplicity space of the unitary group is acted on via the permutations of the symmetric group, and that lambda here is the shared irrep, the shared Young diagram. So this is what I mean by it's very interesting that the symmetric group and the unitary group share the same representation theory with this duality.
How does that get rid of the dictionary?
Yeah, so this, I mean, you have to look at the proof, this double commutator proof. This is in the paper,
Okay.
but it's you basically look at it's basically that the action of this is always the same dimension as the multiplicity of this.
Mhm.
So you use a dimensionality argument that like that for example, say if this is the permutation of 4 elements. Oh, I don't know what it is in this case. For example, let's say this is a permutation of 4 elements, and this had a multiplicity of 4. The multiplicity of this gets permuted by this, and you can use dimensionality arguments to pair up the irreps in that case. Yeah, the proof's kind of annoying in like abstract algebra, but often people just use this as a result and then just say you have multiplicity-free irreps. But I think this is just nice to have this kind of tensor network interpretation of this, I think. Okay. But yeah, so this is short duality, and you have all these different, so you have like this symmetric group irrep, symmetric group irrep, and then you have all these mixed symmetry irreps, and then you have this anti-symmetric irrep. We're only focused on the fermionic representation, so we actually only care about this guy here, which is the anti-symmetric representation. And importantly, you have the symmetric group representation, which carries anti-symmetric symmetric group representation, carries an anti-symmetric unitary group representation. And essentially, this is where things get a little bit technical, I think, but the full fermionic Fock space can be expressed as an exterior product of the n-dimensional single particle Hilbert spaces, Hn. So what this wedge product with a dot n, this is basically saying it's the direct sum of the particle number spaces k up to n, which have these these k-dimensional wedge products acting on them. So that this k-dimensional wedge product here is this famous. You may have seen this as another form of the stated determinant, but it's a kind of a mathematical physics way of writing that.
So Nathan, is this basically saying if you wanted to build a very large n particle, very large Hilbert space, you couple it into all possible sub-partitionings of the smaller, basically giving a number of particles to each of them,
exactly.
And then anti-symmetrize.
Yeah,
that's what that. That's what
exactly.
Okay.
So you anti-symmetrize each particle subspace on each particle number, basically. So this is the anti-symmetrization operator, and it's summing up those. It says this forms a Fock space, and then you get a direct sum of Fock spaces. The full definition of this actually goes to infinity.
Yeah.
In line. But because we're working with a finite basis on quantum computers, I truncate it at n. Okay. Okay. Now, importantly, we're projecting into the anti-symmetric space for each particle number, but that space that's projected into carries a representation of the unitary group of n matrices. So this is really important. So we basically lose the symmetric group information, but we gain the unitary group information. And what happens is when we do this simultaneous projection into each of the particle number subspaces, we get the irrep, which is the anti-symmetric irrep, which is due to the Chauval duality of the unitary group for each particle number subspace. So that gives us for the 0 particle, the 1 particle, and the 2 particle, etc. We can fill these up with these are these short. These become these irreps. The characters of these are represented by these Young diagrams in the same as before, but we're just only using these vertical Young diagrams because we're in anti-symmetric unitary group representation. And the sum of these spaces basically adds up to 2 to the n. And this is like the famous Fock space decomposition. Yeah. Any questions on this so far? Because it's quite technical. But yeah, this basically shows you get the part of the Fock space decomposition with particle numbers. And so we look up here first before we get onto this stuff. These vertical Young diagrams, if we had in the case of if n was 4 here, and we have this 3 vertical one, the number of ways of filling this is 4 different ways. And this basically is the dimension of your particle number antisymmetric space. And these vertical diagrams correspond to the antisymmetric unitary cube representation. The characters of this are a very special short polynomial called the symmetric, the elementary symmetric polynomials. So this very scary looking. So this basically what this is saying is taking the character of the Hilbert space projection, the k-dimensional Hilbert and symmetric Hilbert space projection, and you get the character of this is basically this EK is basically showing you this example. So this sum is basically saying that you have to obey the strictly decreasing semi-standard Young conditions, or strictly Cohn decreasing conditions, for all possible or the sum of all possible combinations of that. Okay. So this is a very special polynomial called the elementary symmetric polynomial. Now, this is just for the k particle space, EK, but we showed that the projection is actually a direct sum over these k-dimensional, or this k-ordered wedge product of the n-dimensional Hilbert space. So basically what this does is it gives you a sum over these EKs for the n-dimensional unitary representation. And this is a very special function called the generating function of the elementary symmetric polynomials. And this is represented with this very simple product here, which is it's a very powerful identity. And what this is showing is it's just the trace of full fermionic particle number decomposition. This whole matrix here. Okay.
And I think the number of variables in your elementary polynomial is it literally the number of particles in your Hilbert space?
So it's the dimension of your Hilbert space.
It's the dimension.
But then that gets filled up with number of particles k.
But like on
So each term in the polynomial has k variables, but they're picked out of n particles.
So
N options.
Each term in the polynomial has k blocks, but they're all filled with the n variables. So you get k different fillings of
up to n.
So you get k blocks that are always filled up with the different blocks of k always filled up with n variables.
Yeah.
Rowan has a question.
Yeah. Right?
Yeah,
Online?
Can you hear me? Can you hear me?
Yeah.
Yeah. So do you use specifically in this these identities that it's an exterior algebra as opposed to
This is an exterior algebra, yeah.
Yeah, but so normally I think of the fermionic Fock space as not the exterior algebra, but as the anti-symmetric algebra.
But I think the exterior algebra is the graded anti-symmetric algebra, I think, which adds this direct sum over the particle number subspaces.
Yeah, so you identify basically x tensor x with 0, and in this symmetric case, it's x tensor y is the same as y tensor x. I'm just curious if this argument carries over to like the symmetric case. So not fermionic, but like bosonic, for example. Like in other words,
it does.
Okay.
It's a different generating function. It's called the complete symmetric polynomials. Yeah.
Okay.
Yeah. So it's rather than being the vertical ones, it's the horizontal ones, and you get all of the same
Okay.
conditions.
Okay, nice.
So you could do bosonic stuff with this probably as well. So yeah, so the Hilbert space is n-dimensional, and then we get the sum of EKs, where the Ks are the number of blocks, but they're always filled up with n variables. There's just lots of, because you have different blocks, the number of ways you can fill the blocks changes with the number of blocks that you have. So this, we haven't done anything with spin yet. This is just a cool way of generating the character of the particle number of fermionic Fock, the full fermionic Fock space. But the main point is that we have this, the trace of the representation is this special generating function of the elementary symmetric polynomials. It's not quite that. There's normally another thing, but it doesn't matter. There's normally an extra variable here, but we don't need to go into that. So this is the theorem that we use. So now we basically identified. I'll prove this in a second. I'm just stating a theorem. So we know that all we've spoken about so far is the Hilbert space of n particles. That's saying fermions can be any of these n things. But we know from the Paldus principle that molecular electrons like to live in these spatial orbitals. So you have d spatial orbitals and then the two-dimensional spin Hilbert space. So really, the space that the molecular electronic fermions live in is this d-dimensional Hilbert space crossed by this two-dimensional spin Hilbert space. And when you have this, there's a very famous decomposition called Howe duality, which allows you to subduct down the group chain from the U2D, which is before it was n, now it's 2D. It is 2 times the number of spatial orbitals. You can break down this. You can go down to a subgroup, and then that breaks up into these 2 conjugate representations, lambda dash and lambda, and essentially these partitions. So that the basic UD cross U2. U2 can't have as a partition that can't. Lambda K is a partition that can't have more than two rows, and lambda D is a partition that can't have more than D rows. And this basically gives you this decomposition under space and spin. So this will make more sense when I show the proof.
And that gives you your irreps.
That gives you the irreps, yeah. The space and spin irreps, yeah, exactly. So that's the theorem. And I think I actually came across this before I found the theorem. I thought I discovered Howe duality, but I figured that it was done beforehand. So yeah, so this basically when you do this exterior product decomposition over HD cross H2, and then you take the character, we basically take that generating function of elementary symmetric polynomials. So if we go back to this guy, but now because we're not in a Hilbert space of n, we're in this direct product Hilbert space. Then essentially this identity then becomes this, which is now broken up over d, sum over I for d, which are the x variables of the I are the trace of the d-dimensional standard irrep, and the y variables are the trace elements of the two-dimensional standard irrep of the U2 group. This is a very famous identity known as the Dual Cauchy identity in symmetric polynomials. So it's essentially when you get this symmetric polynomial, when you get a polynomial in this form, it has a very famous decomposition into this product of 2 conjugate Shor polynomials, where you can't have more than 2 rows on this side and more than d rows on this side. And this is the character. Because these are Shor polynomials, these are the characters of the representations, and therefore this gives you the complete. This simple identity gives you the complete decomposition of the fermionic vector space in the spatial orbital case of d cross HD across SG2 of this HD across H2 Hilbert space. Yeah. So this is the fermionic spatial orbital decomposition, basically. But yeah. So we use the characters to prove this. This is very complicated. Now, hidden within this, you might notice there's a recursive structure, which I had worked a lot on the U-group approach in my PhD, and like I felt like it wasn't that rigorously proven. It was kind of known about, and there was lots of intuition about the problem. But I'd never seen, even from Paldus and Shavitt, a full proof of where the Shavitt graph comes from. So I had to prove. This is basically why I went to all this effort with the symmetric polynomials, is to derive Shavitt branching, and it actually emerges very elegantly out of the recursion of this dual Cauchy identity. Yeah. So if you take this product over D, which breaks up into here that's lambda. If you take out one of the factors of the D, you end up with these. This is just an example of one irrep of the UD case, but you can these mu's of the UD minus 1, and essentially what I mean when you take this out, you get these 4 terms. And these 4 terms are basically correspond to the branching on the Shavitt graph. So I think this goes back to your point earlier, Alex, is that when you're working with a linear set of equations, but you can express these polynomials in terms of these 2-dimensional Young diagrams. Yeah, we had to basically prove that this equals this, and it was a bit complicated. But we state this as a theorem with the proof in the paper. But yeah, we basically proved the Shavitt branching. Which is pretty cool result, I think. But yeah, it comes from this recursion and taking out one of the terms of the recursion, and you get these 4 different ways of combining. So you can see here we got the identity operation. We've got adding 1 box to this side, and the conjugate one here, and 1 box to the right hand side, and then 2 boxes. I won't go into the star and D notation, but the star notation is Poiret rule coupling, and the D coupling is the U1 cross U1 coupling. Yeah. Okay. Anyway, so that's pretty cool. Now, yeah, and this is precisely an example of kind of this subduction chain. So when you have you might have representation of your group G. But under the subgroup H, that vector space might break down into smaller vector spaces, VI, and that's kind of what this notation means here. And yeah, so this is precisely what Shavitt branching is. It's a recursive chain of what's known as a Rotelli diagram. When you have this recursive group representation structure, you get this branching, and that leads to this famous Shavitt graph. So some of you might have seen this in the paper. The 4 possible branchings out of each node. Well, so first let me say then, because we have the conjugation between the 2 irreps from the UD and across U2, we only need to represent the UD one. And we get this ABC notation, which is saying the number of doubles, the number of singles, and the number of empties. That gives us this ABC notation, and that's basically what labels these nodes. And then the 4 possible ways of branching between them we proved before. Yeah, and it basically this is the structure that emerges out of that dual Cauchy identity. Yeah. Then this is the 3 spatial orbital example. Yeah, okay. Now, if we pick one node, this is the 1-1-1 case, and we work out all the pathways to that node. If you see this, the blues here is adding two boxes. The yellow is adding 1 box to the left-hand side, and the green box here, the green branch here is adding 1 box to the right-hand side. All the different possible ways of doing this builds up the dimension of the the representation, basically. And this is a very famous basis called the Gelfand-Zeppelin basis. So yeah, so the paths along the nodes end up with this very powerful basis, which is a branching chain along a unique branching chain along the irreps of the subgroups of the unitary group. Okay, so that was kind of complicated, but basically, if you can now this is slightly technical, but when you have UD, we have UD cross U2. SU2 is a subgroup of U2, and basically what that means is that you can relabel the ABCs in terms of total particle number and total spin, and then the total spin has multiplets of 2s plus 1. And you can't really see it, but this is 6, 0, 1. So that's 6 particle numbers, 0 spin, and 1 spin multiplet space. 5, 4. We basically relabeled them with for total particle number and spin. And this basically recovers exactly these boxes. Okay, so this doesn't make a huge amount of sense, but I think with an example. Okay, well, let me just, yeah. So this is basically showing why you can branch from U2 to SU2 is that when you take the U2 characters with that scary formula, and then because you know that the characters of SU2 are just are traceless, so the representations of SU2 are traceless. This is the complex conjugate. It basically means you can replace this. You can take this equation and replace the lambdas with minus lambdas and the ones. Yeah. And then basically you recover the characters of SU2 from U2. But that's showing why you can do this branching rule. Anyway, that was a bit complicated, but basically you can see, so taking on these blocks, these spin blocks, we have, this is the n equals 3 example, and we know that because we have 3 blocks here. And in this case, this tableau has the conjugate tableau of U3 and U2 are the same. But as we showed before in our branching example, going back, there's 8 different ways to branch to this head node, which end up with these 8 different tableaux. That gives the dimension of these blocks. And we know that the U2 part, basically, because you have 2 blocks on top and 1 block on the bottom, and there's that subgroup, there's that subgroup relation I just showed. It means that this U2 block structure is a total spin of 1/2. And then we know that the spin multiplets of S are +1/2 and -1/2. So that's why you get basically 2 of these 8-dimensional spaces. So you get these coupled to 1 of these each. Okay. All right. So that was a lot of technicals. Now I think we could kind of skip to this part, I guess. So this is really basically the main point is that along these branching pathways, we've shown through the way you can trust me, I guess, that this carries a coupling of SU2. Okay, so this is like genealogical coupling, but rather than just having addition of 1/2 a spin or -1/2 a spin, we also have the opportunity to add an empty orbital and a doubly occupied orbital, both of which don't add to the total spin because the doubly occupied is spin paired. So it's kind of an extended genealogical coupling. And this was first represented via, I call it Paldus Boyle SU2 spin coupling, because this paper in 1980 was the first they kind of realized this. Basically, each arc, you might notice here, there's some numbers. So there's these 4 different branching strategies that we derived before. Each one of these branches, the 0 branch, the red one, I'm going to call this red, yellow, green, and blue, just for clarity. The red one doesn't change the total spin, doesn't change the particle number. The yellow one adds a particle. but also adds half a spin. The green one adds a particle. So these up here, these are n. This is n plus 1. It adds a particle and removes a spin, and the blue one adds 2 particles and doesn't change the spin. Okay. And then there's a corresponding spin coupling when you do that in the spin projection space. So essentially, you have to think about it as two corresponding graphs. You have the UD part of the graph and then the SU part of the graph. The SU part of the graph can be thought of as the genealogical coupling, and these are the Clebsch-Gordon coefficients here essentially. So when you add a doubly occupied orbital, the blue, and a single and unoccupied orbital, the red, you have no Clebsch-Gordon coupling because you're not coupling a spin. But when you couple with plus a half and minus a half s, you end up with these Clebsch-Gordon couplings. And I think this is not well known by Paldus and Ball, but they have this really elegant sinusoidal, theta representation where they all behave like as part of an RY matrix basically. Mm-hmm. And so if you think about these nodes on the bottom, this is this vector, and they get coupled by this Gibbons rotation matrix, so they form the nodes on the top, which is this guy here. So basically, this coupling you can represent in a Gibbons rotation matrix, which is a very important thing. It means building a quantum algorithm for this is probably going to be a bit simpler. Now, that's very complicated. I have some examples, which kind of makes it a bit clearer. So in the last lecture, I showed you about the classical, just spin up, spin half, spin plus a half, spin minus a half, genealogical coupling. But here we've got these 4 extra cases. So in this case, it is just spin plus a half, spin plus a half, spin plus a half. Sorry. So this is a very scary looking equation up here. The nodes of this graph, these are labeled by S and N. And the pathway to each node is labeled by a D. And then each node on this spin projection graph, MZ, is labeled by M. So for example, and this very scary looking equation is basically saying, as you walk along this graph, we add up all the pathways to a certain N value, say this one. And that's what this C is here. So these C's are just the arc values on this spin projection genealogical coupling graph. And you basically get all these different spin couplings as you traverse the GT graph, the UD Gelfand-Zetlin graph. And this is coupling a spin, alpha beta as well. So this is just genealogical coupling with an extra bit of, with the ability to not couple an orbital, so a couple of doubly occupied orbital and empty orbital, spatial orbitals. All right, so we have a bit of time left. That's good. So the game really with the quantum is basically how do we get a quantum algorithm which traverses this graph but correctly applies the spin coupling to the computational basis. And that's what we figured out basically. So this took me 5 years. As you can maybe tell. But with the help of Jed, who came up with the quantum algorithm side, we managed to figure this out. So basically, there was this algorithm called efficient quantum circuits for Shor and Clebsch-Gordon transforms by Dave Bacon, Isaac Chung, and Aaron Harrow in 2006. That is for the symmetric group crossed with SU2. We were very inspired by this to basically take that structure and apply it to UD cross SU2. And it's a recursive coupling of basically these X1 up, X1 down. You basically add a spatial orbital, and then you apply the correct spin coupling to that indexed on your M, S, and N values. So I'll explain what all these components are in a second, but you can see that it's a recursive algorithm that happens. You just by adding a spatial orbital, you just apply the right spin coupling.
So is each of them can register a spatial orbital?
Yeah, exactly. Yeah. And then the output here is a pathway. So you input the spin, the spatial orbitals. You apply the coupling correctly, and then the output basis index is D, capital D, bold D, which is different to the number of spatial orbitals. And that is the capital D is basically the path on this graph. So you get like 1, 2, 1, or 1, 1, 1, or 1, 1, 3, etc. 1, 0, 1. So yeah, it's just a basis transformation into the basis of the spinor coupled representation. And so basically we have to map the registers, so N, S, and M, onto qubit registers. So this is a simple example. So for a maximum of 4 particles, we can index that in binary this way. And then we index the spin registers, which are half integer increments in the same way. But obviously, because the spins go from plus S, M's go from plus S to minus S, plus S to minus S, we need a bigger M register here. And basically, each one of these inputs, basically each one of these this is what I was saying before. Each one of these, every time you add a spatial orbital, you have to correctly traverse the branching on this side, which means getting you have to change the N values correctly. You have to change the S values correctly. So this is what this one, S values get changed here. The N values get changed by this guy. So these are incrementers, I'll show you in a second. And then you have to change the M values correctly on this side. So basically, the branching is done by these C0 increment, these incrementers in our notation, and then you apply the correct theta value for the various spin coupling that you're doing, with the control Gibbons rotation indexed correctly on the S and M dash registers. So I will go through each step. So yeah, if we're trying to traverse graphs, if you're going to take one thing away from this talk, controlled incrementers allow you to traverse graphs on a quantum computer. So in the notation we're using here, it's a little bit sloppy, I apologize, but we're replacing the C0 now is an incrementer because this is a register, and this notation is just like an extension of the C0 to like a register. But what this XOR means here is basically if we take say if we have an index register of 8, so we have a target register of 3 qubits, so 8 possible basis states. So that basically means we have 0 to 7 integers held within this register. If we go in with a 1, you can see that if this bottom one is a 1, that means we're going to fire the incrementer. This incrementer is going to fire. And this one will flip, so go to 0. Yeah, and then this one flips. So it goes in reverse. So you see what I mean? Yeah, yeah. And so basically, you're just shifting the register up by 1. This is what Chiara is an expert on. There's this compilation strategy. So there's a way to compile these with 3n operators, 3n key gates, where n is the number of qubits, with log n clean qubits. So this is this new, this is paper by Craig Goodney in 2014. Now when we traverse this graph, we have 3 different kind of traversal conditions. We traverse on the N, we traverse on the S, and we traverse on the spin projection. So if we look here on this branching, you can see the 0, the red takes the N, doesn't do anything. The red takes the N plus 1. The yellow takes the N plus 1. The green takes the N plus 1, and the blue takes the N plus 2. So how we do this is we just apply. This is our spatial orbital coming in here, and basically when this is 1 and this is 0. So when this is 0, 0, we won't increment. The incrementer won't fire. So we get n plus 0. When it's 0, 1, one of the incrementers fires, and the other one doesn't. And the same when it's 1, 0. And when it's 1, 1, both incrementers fire. So hopefully you can trust me that this is doing the index. It's just changing the indexes in the correct way as it's branching across this graph here. And this is basically double the cost of a single incrementer because we've got 2 incrementers. Now for the S stepping, the S traversal on the graph, it's a similar idea. The red takes S to S, the yellow takes S to plus S, the green takes S to minus S, and the blue takes S. It doesn't do anything. That should be S there. Sorry. But you can see that again we do a very similar idea, but rather than I'm now indexing it as a half because it's just how the register is indexed. But all we do is we basically have one incrementer going forwards and one incrementer going back. So if we see that if 0, 0 happens, again nothing happens. 0, 1 happens, which is this guy. If this is 1, this will go plus half, and this is 0, this one won't fire. Now if this one is 0, which is this case, and this one is 1, then the increment goes minus a half. And then if they both fire 1, 1, you plus a half and minus half, you end up with 0 overall. So that's correctly satisfying the S incrementation conditions here. And it has the same cost as 2 incrementers here. And it turns out that the M incrementation, even though it's a different graph, it has the same incrementation structure because we have 3 different inputs. So we have M plus 1/2, and M minus 1/2. They all end up in M at the end, but they have different inputs, 3 different inputs. And essentially, if you work this out, this incrementer correctly satisfies this branching strategy and has the same cost. Okay, and then the control Gibbons rotation, you might think about this as being quite a scary looking thing. This is once you've done the branching, or as you're branching, you have to correctly apply the spin coupling via this Gibbons rotation matrix, which you pre-compute all the thetas. And this Gibbons rotation matrix has this quite nice RY structure. Now, naively, you would what these boxes mean is just a control register of all S values and M values. And then you have a Gibbons rotation for the various S and M values. Because this is an integer. This is a half integer, each one of these control strings, and this is a half integer. And you have a Gibbons rotation for each one of those. Now that's like a nasty circuit, but it turns out that you can actually pre-compute and store the rotation via this QROM in a fault tolerant setting. You can do it with this QROM construction. And essentially, someone told me this is linear, but I don't trust them. I think it's quadratic. But you basically, what you do is you store, for each S and M, you store the theta as a binary incremented rotation. Okay, so like if you can see that we have a pi rotation, pi over 2 rotation, pi over 2 cubed to the minus 1 rotation. And those fire depending on whether, so each one of these is a rotation. So if this is 1, 1, 1, all of these rotations will fire and we'll get like almost a full circle. And what this means is you only have to do order 1 constant depth Gibbons rotation at the expense of storing the QROM rotations in a uni-iteration compiled multi-controlled register. So this compilation is I just had it here. So when you have these strings of multi-controls indexed over, so I like to think of these as for loops in a quantum computing setting, is that you're looping over all of the control indices in this binary setting. And then you have this target register of these U's. So you're looping over all the U's basically. Basically what happens is you can take, there's this famous, you can't really see this here, but this is when you have these multi-controls, you can add NC is the number of controls here. You can add NC minus 1 work qubits, and then you can do a Toffoli cascade for this. And when you put the Toffoli cascades together, I don't have time to show the full, but you basically get all the adjacent Toffoli ladders cancel, and you end up with basically linear scaling multi-controlled operations. So this is why the QROM case is actually quite cheap, even though it looks quite scary. Yeah, cool. So that is the end of my talk. The future directions. So this basis is very lucrative, I think. There's a lot of work to be able to figure out how to map into the spin adapted UD cross SU2 basis. But really, the motivation for me is when we're in this basis, it allows us to directly calculate the matrix elements in this graphical framework, directly as a graph. And I really want to be able to figure out a block encoding in this framework. So this to forget the numbers on these nodes, they're just wrong. I didn't have time to fix it, but yeah, basically I want to be able to figure out, once we're in this basis, I want to be able to calculate the matrix elements directly as walks on the graphs that we calculated before. And I guess the prize for this is that when you have the attribute matrix elements and they act on this Gelfand-Zetland basis, you can calculate the full set of operators from these elementary generators which scale linearly. So it points towards there being a linear scaling compilation of the molecular electronic Hamiltonian and block encoding. So this is really what I'm trying to attack, is like being able to work with these matrix elements with just the elementary set of generators. So yeah, and that would be a much cheaper block encoding, I think. So yeah, that is the talk finished. Thank you for sitting with me. Very heavy. I apologise. Yeah. Well, hopefully, if you read the paper now, it might be slightly less difficult to read.
So Nathan, can you then, effectively, when you block diagonalize, sometimes life is nice because you can then throw away some of your blocks. And I couldn't quite see where you do that selection, where that was to reduce your qubit count, maybe.
Yeah, good point. Yeah, so you can certainly post. Oh, where am I going?
Yeah, post selection.
Yeah, so you can post select out or project out the block of interest. So if we go back to the transform. Yeah, so you basically end up indexing. So this is your state register.
Yeah. And
what the outcome of this transform allows you to do is we basically indexed on total particle number, total spin, and spin projection. And these are binaries which index your particle number, spin, and spin projection. So you could just pick one of these binaries, and that'll project you into the particle number block. It doesn't give you the same kind of, like, you can't throw away operators in like a Jordan-Wigner encoding or something. This is more of a deeper, like you're really like transforming the whole space which the wave function acts on. So this is, the construction of the matrix elements in this framework is still a bit confusing to me.
But it looks like, because effectively you can traverse all paths at the same time, which is the sort of thing you can do here.
Yeah.
You can create effectively entire blocks of matrix elements together at the same time.
So that's a fantastic point, and that is something we've been trying to think about. Is like this allows you to coherently project into each block at the same time. So you could do phase estimation in all of these things at the same time. And then I just don't know what you would do with that. Can you recombine them and do something with that? It's an open question, I think. But yeah, this is a coherent algorithm. So you basically block diagonalize, and then you maintain those states. Yeah, and then you can transform back at the end as well if you somehow could manipulate them. Then yeah.
general, like, could you do the same easily for another group?
Good question. So I
Have to do the graphs.
yeah, so you'd have to figure. So I believe the Bertelli. It's a good question. So yeah, these Bertelli diagrams.
Mhm.
This is a completely general group representation theory thing. So
Yeah.
if you can figure out some group chain like this and figure out how to traverse it,
Then the circuit applies.
then you could use some. You have to change the. You have to change the incrementation
Rules,
rules, yeah. And then also the Clebsch-Gordon couplings will be different depending on the group as
Yeah.
well. But remember, this is special because it's a dual group. It's UD plus SU2. And that means that you have finite dimension because you are in the antisymmetric subspace.
Mm.
But like the arbitrary orthogonal group, you have an infinite number of irreps in that case. So you might have to truncate or do some clever truncation. But yes, I agree. If you want to do this generally, I think the main point is the incrementation and the traversal of the Bertelli diagrams is what you would use.
But is it, like, building the diagrams is systematic, right?
Yes.
Okay.
Yeah. I think most of this has been figured out by mathematicians.
Mm.
Yeah.
So then could you transform your the point group symmetry group action things into this sort of diagram as well? And would that be more or less efficient than the,
I think there is a. This is very special because this does the Shavitt graph construction, but I think there are similar subgroup towers within the point groups. Like you start with like spherically symmetric, and then you add further and further constraints, and you have the subgroups. I think it is a general recipe, yes, to build groups. I think that's how they do it in math, in like group Fourier transforms as well, like in the classical space, is that they use these Bertelli diagrams.
Mm.
Yeah, I think it's general. This is a dual group, so it's special. But these incrementation things. As long as you have a subgroup chain, you should be able to use this idea. I think. Yeah.
And there's a paper called like quantum short transform or something.
Yeah. This one
Where-
probably.
I thought that they were doing it very differently, but is it like, are they doing the same thing?
Yeah. So there are like quantum algorithms papers which state this can be done asymptotically more efficient using like products of the quantum Fourier transform.
Yeah.
Jed's the guy who talks about this. I don't really believe those are valid approaches because no circuit has been presented in that case. So that's just my view. Like it's not been compiled, so I don't trust it. Basically, yeah. This is a rigorous compilation strategy we use.
Yeah.
I'm like, if you wanted to try and use those ideas in this framework, that would be a really good paper.
Yeah.
Yeah. Pretty hardcore, though, not gonna lie.
But it would be on O3, so that's also why I'm asking.
Yeah, I think Jed knows quite a lot about that kind of stuff.
And like, do you think a way of building something similar could involve addition of angular momentums?
Yeah, I think so. I mean, this is just additional angular momentum, these given rotations.
Yeah.
And I can.
But
That's
the
why.
way, because you go through the diagrams to build it, but could you just go through the operators instead? It would just be more of a pain.
I don't know. That's that question. I will say that Frank Verstrassen over in physics, like he's come up with this representation theory for tensor networks. He was very interested in this because all of that work is essentially using what's called the Wigner-Eckart theorem to decompose your matrix product operator into a symmetric part and then the variational part. This is an example of the Wigner-Eckart theorem. So UD and the SU2 part of the factorization. So if there was a general recipe at the operator level, it would use Wigner-Eckart theorem. I think. Yeah.
Since we need extra qubits to do this Paldus transform, will we expect that to translate to even more into the qubits from locking coping as well?
I would say that once you're in the basis, I would hope that that's fine, but I don't know the answer to that. Well, I haven't figured it out yet.
Okay.
I think that sounds like a good intern project. But yeah, the blocking coding is the next step, and I would hope that it's cheaper than all the modern approaches.
It should be because you
Yeah.
have fewer different numbers in it, basically. So,
Yeah.
yeah, because you don't have so much cancellation, which means you get small or large numbers, and you just apply one number depending on what
Yeah.
path you go. So,
My intuition tells me that this will end up with the optimal blocking coding because there's been no blocking codings which rigorously treats spin symmetry. There's lots of these approaches which require this block invariant symmetry shift, which combine double factorization and tensor hypercontraction, and they're just like they're quite numerical in the sense that they just mangle the Hamiltonian to move the symmetry checks out. This is a much more elegant approach to symmetry, in my opinion. Yeah.
Thank you, Nathan.
No worries.
Thank you.
Thanks.